Welcome back to the Deep Dive. This is where we distill your sources, cut through the complexity, and deliver the intellectual shortcuts you need to be truly well-informed. Today, we are diving deep into the technology that has, well, completely redefined our professional and personal lives. Large language models.
It's fascinating, isn't it? I mean, models like GPT-4, Claude,
Yeah,
they're just everywhere
it's
now.
everywhere.
We use them for brainstorming, for writing code, summarizing reports, and they feel incredibly competent almost. Well, magical.
That's the word, magical. But for most of us, that competence is hidden behind this complete black box. We don't really get the mechanics.
Right.
The systems appear to reason, they seem to create, and they appear to hold just vast amounts of knowledge. But we know they aren't human. So what are they?
And that's the big question.
So our mission for you, the learner, is to go beyond the marketing hype and to really understand the absolute foundational pillars that allow these models to function. We're going to break down, let's call it the physics in the system.
I like that. The physics.
Yeah, we're talking tokens,
Yep.
embeddings, and the revolutionary transformer architecture.
And we've analyzed the source material, and what it emphasizes over and over again is this. LLMs are not sophisticated thinkers, not in the human cognitive sense anyway. They are, at their core, just astonishingly sophisticated pattern-matching machines. They've learned the statistical relationships in massive, massive quantities of human text.
That distinction, statistical pattern matching versus, cognitive reasoning, that feels like the key to understanding both their power and their limitations.
It absolutely is.
We want to give you the blueprint, the how. How did this convergence of innovations result in the powerful AI we see today? Let's stop talking about the magic.
And start talking about the engineering.
Exactly.
Yeah.
Okay, so if we're going to understand the engine, we have to start with the fuel. And the fuel is language.
Right.
When we interact with an LLM, we type in a prompt, a sentence, a paragraph. And I think a common misconception is that the model processes this text letter by letter, or maybe word by word.
Which seems intuitive, but it's not what happens.
So if that's wrong, what is the smallest unit of information the model actually consumes?
They are processing tokens. This is the absolute starting point for any large language model.
Tokens.
A token is a foundational unit of language, but crucially, it is a subword unit. So it can be a whole common word, sure, but it can also be a partial word, a piece of punctuation, or even a space attached to a word.
Okay, let's unpack that right away.
Yeah.
Why bother with subword units? Why not just use whole words? It seems like an unnecessary complication right at the start.
Well, the primary reason, and this is a really important technical shortcut, is vocabulary efficiency.
Vocabulary efficiency.
Yeah, just think about the scale of human language. If you tried to catalog every single word, every tense, every proper noun, every compound word, and then every potential misspelling.
Across all languages.
Across all the languages these models need to handle, your vocabulary list would contain literally millions, maybe hundreds of millions of unique entries. And that list would just be impossible to manage computationally.
So by breaking things down into these smaller chunks, you get incredible coverage with far, far fewer fundamental units.
Exactly. The source material highlights that most LLMs operate with a fixed, manageable vocabulary of tokens, usually somewhere between, say, 50,000 and 100,000 unique tokens.
So that's it, just 50,000 building blocks.
And that fixed set of 50,000 units can represent virtually any text ever written. It dramatically simplifies the mathematical structure the model has to learn.
Okay, so how does the model actually decide how to break a word down? What is that tokenization process?
It's a statistical process, and it's driven by the model's training data. The tokenizer is designed to be highly efficient. So if a word is extremely common, like the hello or cat, it's almost always stored as a single token.
Okay, that's just efficient to access it that way. A single token for a single common word. That makes sense.
But if you encounter a longer, less common, or a morphologically complex word, the tokenizer is designed to split it. It splits it into the largest possible known subword units.
Got it.
So take a word like complexities. It might be split into 3 tokens. Complex, it, and ease. Or the example from the sources, unhappiness, which would probably be split into the prefix un plus the root happiness.
I noticed in the examples we looked at that the tokenizers often attach the space before a word to the token itself. So the phrase deep dive would become something like deep dive with the space leading the second token. Why is that? Why is that space inclusion a technical necessity?
That's a crucial little detail for maintaining the structure of the output. When the model is generating text, remember, it's predicting the next token.
Okay.
By attaching the space to the token, the model is inherently predicting not just the word, but also the punctuation and spacing needed to separate it from the previous word.
Oh, I see. So if they didn't do that, the model would just generate a stream of text where all the words run together, like this alone word.
Exactly. It forces the model to preserve the cadence and the word boundaries of how humans actually communicate. It's a very elegant, practical solution for formatting.
It is. Okay, now let's get to what seems like the real power of this subword unit approach, handling the unknown. If the model has a fixed vocabulary, what happens when it sees a brand new word, say a new internet slang term or a highly specific medical term it's never seen before?
This is the moment where the tokenization strategy just shines. The model doesn't fail, it doesn't crash. It uses its fixed vocabulary to synthetically construct the unknown word. It decomposes the unfamiliar word into known components.
So it builds it from parts it already knows.
Yes. Let's use that specific example from the source material that illustrates this decomposition. Take the word unbelievable.
Okay.
Now, if this full word was rare, or if the model just hadn't seen it enough in its training data, the tokenizer would break it down into units the model does know. Something like unbelievable.
So even if the entire word unbelievable is new, the model immediately recognizes the prefix un, which always implies negation, not. The root believe, which is a core concept, and the suffix able, which denotes capability.
Precisely. By stitching together the meanings of these three component tokens, the model can infer the meaning and context of the unfamiliar word, in this case, not capable of believing, without ever needing an explicit dictionary entry for the whole word. This makes the model incredibly robust and flexible.
So it's not a memory retrieval system. It's more like a synthetic construction system for meaning built on these foundational subword units.
That's a great way to put it.
And that also explains why they're so good at languages they weren't explicitly trained on, right?
It does. The final bonus of this whole approach is multilingual support. Because so many languages share phonetic sounds or, structural components like prefixes and suffixes,
Right.
a tokenizer trained on a vast English corpus often has a head start on processing a related language like Spanish or German, because those languages also rely on many of the same fundamental subword chunks. It just offers massive efficiency across language boundaries.
Okay, so we've successfully broken our input language into tokens. But a computer doesn't process un or believe. It requires math.
All math.
This necessity transitions us smoothly to the second foundational pillar, embeddings. This is where text gets translated into the language of the machine numerical vectors.
That's right. An embedding is the numerical representation. You could call it the mathematical fingerprint of a token. It takes a discrete text unit and converts it into a continuous numerical format, usually a dense vector.
And when we say vector, we're talking about a long list of numbers.
A very long list of numbers, often hundreds or even thousands of dimensions long.
Thousands of dimensions. That sounds highly abstract. I mean, we can barely visualize 3 dimensions. Why do we need so many numbers to represent just a single token?
The sheer number of dimensions is necessary because each dimension represents some nuanced aspect of the token's meaning or its context or its relationship to other words. But the genius here isn't the list of numbers itself. It's the way that high-dimensional space is organized.
How it's structured.
Yes. This is what we call semantic geometry.
Semantic geometry. That's a wonderful shortcut term. Explain what that means in practical terms for the listener.
It means that the location of the token's vector in this high-dimensional space literally represents its meaning. Words that are used in similar contexts, words that share similar semantic meaning, literally sit closer together geometrically in this space. Their vectors point in similar directions.
So the vector for cat would be near the vector for dog, and the vector for blue would be near green, simply because they're statistically close neighbors in the training data.
Exactly. But it goes deeper than just being close by. Embeddings capture analogies and functional relationships through, believe it or not, vector arithmetic.
Math.
We have the classic analogy. If you take the vector for the token king, subtract the vector for man, and then add the vector for woman.
Okay.
The resulting position in the space is almost identical to the vector for queen.
That is the ultimate aha moment. It means the model has mathematically learned the abstract concept of gender difference and applied it analogously across different concepts, like royalty, without being given any grammar rules or dictionary definitions. It just figured out the function.
It has discovered the inherent structure of human language just by reading billions of pages and trying to predict which word comes next. It's capturing analogies, tenses, pluralization, functional relationships, all of it encoded in these spatial relationships.
So if they aren't programmed, how does the model figure out where to place those 50,000 tokens in this mathematical space? How does it build that map?
They're entirely learned, not programmed. The process, it starts with chaos. When the model is initialized, the vectors for all tokens are assigned random numbers.
Random numbers for king and queen. Just noise.
Precisely. Then the vast pre-training phase begins. As the model iterates through millions and billions of text examples, constantly trying to minimize the error of its next token prediction, it subtly adjusts these random numbers.
A tiny little nudge each time.
A tiny nudge. If the model incorrectly predicts the next word, the vectors of the involved tokens are tweaked slightly to reduce that mistake in the future.
This sounds like continuous, massive scale optimization.
It is. Over time, because king and queen appear frequently in similar royal contexts, the optimization process naturally pulls their vectors closer together. And because king and man share a masculine association, and queen and woman share a feminine one, those functional relationships emerge mathematically. The training process effectively sculpts the random chaos into this highly ordered, meaningful semantic geometry.
Now we need to introduce a crucial distinction that separates today's powerful LLMs from earlier pioneering models. We need to talk about fixed versus contextual embeddings.
Yes, this is a big deal. Older systems like Word2Vec used fixed embeddings. So if you had the word apple, the embedding vector generated for that token was always the same.
Always the same.
Whether you're talking about Apple computers or eating an apple. And this caused a lot of problems because, well, language is inherently ambiguous.
A word's meaning is derived entirely from its surroundings, from context.
And modern LLMs solve this with contextual embeddings. In these models, the embedding for a token is not fixed. It's dynamically generated during the processing of the input, taking into account the entire surrounding sequence of tokens.
So the word apple, used in a sentence about technology, will be represented by a vector that sits close to software and Steve Jobs. But the same word apple in a sentence about farming will be represented by a vector closer to orchard and fruit.
That's the key technical breakthrough. Let's use the classic example, the word bank. In the sentence, I parked the canoe on the muddy riverbank, the contextual embedding for bank will emphasize its association with water and geography. That vector will point toward shore and river.
But if the sentence is, I went to the bank to deposit a check,
then the resulting embedding for the exact same word will point toward finance, money, and teller. The model determines which specific facet of meaning is relevant based on the surrounding context. This context sensitivity is what allows modern LLMs to handle polysemy words having multiple meanings and thus process nuanced human language with incredible accuracy. This translation from text to meaningful, context-aware numerical geometry is the bedrock on which the next innovation is built.
Okay, we have our tokens, and we have their context-aware numerical representations. The embeddings. Now we need the engine, the power unit that takes those numbers and synthesizes them into understanding.
And that is the transformer architecture.
The big one.
This is the monumental breakthrough. It came from the 2017 paper, Attention is All You Need.
Great title.
An all-time great title. Before the transformer, language models were sequential. They processed information linearly, one word after another, like reading a sentence. But if a sentence was very long, say 50 words, by the time the model got to the 50th word, the memory of the first word was essentially diluted or even lost. They really struggled with long-range dependencies.
They were reading with short-term memory limits, essentially.
Yes, that's a perfect analogy. The transformer shattered this constraint with its core innovation, self-attention.
Self-attention.
Self-attention allows the model to look at all parts of the input text simultaneously when processing any given token, no matter how long the distance is between them.
So it can connect word 1 to word 50 instantly and weigh its importance in the context of word 50. Okay, but how does it determine importance? That's the mechanism we need to demystify.
That's where the QKV mechanism comes in. For every single token entering the transformer block, the model generates 3 dedicated vectors from its embedding. They are the query, Q, key, K, and value V vectors.
Okay, let's dedicate some time to truly understanding these roles because they sound like the heart of the engine. What are these 3 vectors doing?
Let's use an analogy of a group meeting or a consultation. When a token enters the system, it's looking for context. The query queue is that token asking a question. It's asking, what information in this sequence is relevant to me right now?
Okay, so the query asks the question.
Right. And the key, K, is generated by every token in the sequence, and it acts as a label or a summary. It's saying, here's what I am about, and here's how relevant I might be.
Okay, query asks, key answers, this is what I am.
The model then compares the query of the current token against the keys of all other tokens, including its own. And this comparison generates the attention score.
The attention score.
This score is the mathematical measure of relevance. A high score means pay close attention to this other token, and a low score means you can pretty much ignore it.
And what about the value V? That's the third vector.
The value V is the actual content. It's the payload of information the token is offering. So once the attention scores are calculated, they're used as weights to combine all the values.
So the current token's final contextualized output is a weighted average of the value vectors of all the other tokens in the sequence.
Exactly. If the model decides token A is, say, 70% relevant and token B is only 10% relevant, the output will contain 70% of A's value and 10% of B's value.
So that means every single token that leaves the self-attention mechanism is this complex synthesis of the entire context that came before it. It's a dynamic, context-aware representation.
Precisely. Let's look at the classic case of pronoun resolution to see the QKV mechanism in action. Consider the sentence. The sculptor ran out of clay, so he switched to metal.
Okay, so if we are processing the token he, the query vector for he needs to resolve that reference, it starts searching.
Right. He issues its query. It compares this query against the keys of every preceding token. The sculptor ran out of clay. Because of its training, the model knows that pronouns like he often refer to agents who perform actions. So the key for the word sculptor will generate a massive attention score.
While the key for clay will generate a near zero score.
Exactly, because sculptor is a person capable of running out of things and switching to new materials, whereas clay is just the object.
Right.
So the final output vector for he will be heavily weighted by the value of sculptor. The model has successfully resolved that he refers to the sculptor, which is essential for predicting the next logical tokens in the sequence, like switched, which is an action a sculptor performs.
And that's just a single layer of attention. But the architecture is far more powerful because of multi-head attention. Why do we need parallel attention mechanisms? Why can't one head do the job?
Because one head provides one perspective, but language is multifaceted. Multi-head attention is kind of like having a team of experts, each focused on a different type of relationship at the same time.
So instead of one context lens, we have, what, maybe 12 context lenses all running at once on the same input? What do these different heads specialize in?
They capture different types of grammatical or semantic linkages. So, for example, one attention head might specialize entirely in tracking syntactic links. Is the subject agreeing with the verb? Is the preposition correctly linked to its object?
And another head might focus exclusively on semantic links, like our pronoun resolution example, connecting he to sculptor.
And crucially, another might be dedicated to long-range dependencies, connecting a topic introduced in the first sentence of a long article to the conclusion 500 tokens later.
That's incredible.
Each head calculates its own unique set of attention scores and generates its own weighted value output. And the statistic from our sources is astounding. Typical models use anywhere from 8 to 96 attention heads per layer.
96.
Imagine 96 different specialized subcalculations happening simultaneously just to contextualize one single token.
That sheer parallelism is what gives the transformer its enormous power to understand complex structure.
Wow.
Okay, so self-attention is the engine, but it's not the only piece in the block. Let's define the full transformer block.
Right. A single transformer block is composed of 4 main innovations working together. First, we have the multi-head self-attention we just detailed.
Got it.
Second, we introduce layer normalization.
Layer normalization. That's a concept from deep learning engineering. For the listener, why is this mathematical step necessary after the attention calculation?
Well, imagine pouring water through a long, complex pipe. Every time the water moves, friction changes its flow a little bit. In deep learning, as numerical data flows through dozens of layers, the values can shift dramatically. They can become too large or too small, which corrupts the learning signal.
It gets unstable.
Very unstable. Layer normalization is a technique used to standardize the magnitude of the data after each major operation. It stabilizes the signal, preventing the model from essentially getting confused or having its learning signal degrade as it gets deeper.
It keeps the data streams clean and stable so the network can be built deeply.
Yeah.
Okay, what comes after normalization?
That takes us to the third component, Feed-forward networks, FFN. This is a simpler, more standard neural network that's applied to each token position independently. And the FFNs are where the nonlinear transformation happens. The complexity is really introduced here.
What's the function of the FFN then?
If self-attention is about gathering context from everywhere, the feed-forward network is about deep pattern recognition. You could almost say it's like critical thinking for that token.
Okay.
It allows the model to map the contextualized embedding from the attention layer onto even more abstract and complex features. This is where the model learns highly specialized patterns that can't be represented by simple linear attention weights.
And finally, the essential safety net for these deep networks.
Yep.
Residual connections.
Yes. A residual connection is literally a bypass pipe. It allows the original information from the input to skip the entire attention and feed-forward operation and just be added directly to the output.
Why is that so crucial?
Without residual connections, if you train a network with, say, 50 layers, the signal would degrade or get lost very quickly. You'd lose the original data.
Right.
The vanishing gradient problem.
Right.
Residual connections ensure that the core input signal is preserved and maintained throughout the entire processing stack. They are what allow the LLM architect to build models with dozens or even hundreds of layers, like GPT-3's 96 layers, without losing the ability to train them effectively.
Which brings us to the final and most profound point about the transformer: stacking for abstraction. We're talking about dozens of these blocks stacked one on top of the other, each one feeding into the next. How does the function change as we go deeper into the stack?
The sheer depth of the model creates a hierarchy of understanding. The early layers, the first few blocks, are focused on low-level representation. They are capturing the surface elements, identifying basic syntax, capitalization, punctuation, and the immediate local word relationships.
They're just checking grammar and basic word order.
Exactly. Then the middle layers begin to synthesize meaning. They start tracking those long-range dependencies, resolving pronoun ambiguity, and really understanding the semantic intent within a full paragraph. They connect concepts and build a map of the argument.
And the deepest layers,
Yeah.
the ones at the very top of the stack.
Those later layers are handling the most abstract processing. They are the ones synthesizing information from multiple paragraphs, performing complex reasoning, applying learned task instructions, and potentially detecting things like tone, nuance, or even satire and irony. This massive hierarchical stacking is the fundamental reason a model can transform from a simple grammar checker into a tool capable of high-level philosophical discussion or code generation.
We've broken down the architecture. We have the token, the embedding, and this stack transformer engine. Now let's walk through the moment the listener actually interacts with the model, the text generation pipeline. How does the model produce a coherent, sentence-by-sentence response?
It starts with your input prompt, of course, which is immediately tokenized and converted into its context-aware embeddings. But before those embeddings enter the transformer stack, a crucial step has to occur: positional encoding.
We mentioned this earlier, but it deserves emphasis. Why is positional encoding so necessary if the attention mechanism is so powerful?
Because the self-attention mechanism, as powerful as it is, processes all tokens simultaneously. It's inherently order agnostic.
Doesn't know what came first.
Not on its own, no. To the raw attention mechanism, the sequence "John is chasing the dog" is numerically identical to "the dog is chasing John" if the tokens are just floating in the system. The attention scores would be the same.
But the meaning is completely inverted.
Right. Positional encoding solves this by injecting a unique, explicit numerical signal into each token's embedding that tells the model exactly where that token sits in the sequence. It tells the attention heads, this token came first, this one second, this one 10th. This allows the model to factor in sequence order during the attention calculation, which ensures that structure and meaning are preserved.
So the positionally encoded embeddings then flow through the dozens of stack transformer layers we just discussed. They're constantly being refined, contextualized, and abstracted.
Correct. After flowing through the final transformer layer, the output is a highly rich, contextualized numerical representation of the sequence. This is then passed to the final stage, output projection.
What happens during projection?
The vector is projected onto the model's entire vocabulary space. Essentially, the final layer performs this massive, simultaneous calculation that compares the final contextual vector to every single possible token the model knows, all those at 50,000 to 100,000 units.
And the result of that projection is the next token prediction.
It creates a probability distribution over the entire vocabulary. So it doesn't just predict one word, it assigns a likelihood score to every single possible next token.
Every single one.
Yes. So if the prompt was, I enjoyed drinking a hot cup of the token coffee might receive a 30% probability, tea maybe 25%, water 5%, something like spaceship would get 0.001%.
So the model is essentially providing a statistically ranked list of every word it knows, weighted by how likely it thinks they are to come next, based on its vast training data.
That's the most accurate description, yes. The final step is sampling. The model doesn't always pick the absolute highest probability token.
Why not?
Because if it did, the response would be extremely conservative, predictable, and frankly, pretty boring.
This is where the concept of temperature comes in, which is a key control for the user.
Temperature dictates the randomness. If you set the temperature very low, close to 0, the model is forced to choose the highest probability token, making it factual, conservative, and reliable for tasks like summarization or writing code.
Okay.
But if you set the temperature high, the probability distribution is flattened. It allows lower probability tokens to be selected more often.
Which introduces creativity, unexpected connections, and sometimes total nonsense.
Exactly. It's injecting useful statistical variation into the output.
So once a token is selected, what happens?
That new token is instantly appended to the original sequence, and the entire process tokenization, embedding, positional encoding, flow-through transformers, prediction iterates. It repeats instantly, generating text one token at a time.
This emphasizes the concept of autoregressive generation. It's building the output greedily, one token at a time, based only on the statistical probability of what should come next, given everything that has come before. It doesn't write an essay in one go.
That is the crucial takeaway. When you get a coherent 5-paragraph essay from an LLM, it's not because the model had a mental outline and a plan. It's because it executed a chain of hundreds of consecutive, highly successful next token predictions, with each new token serving as the necessary context for the next. The coherence, the narrative flow, it's purely an emergent property of the statistical chain.
So where do these astonishing statistical patterns, the foundation of the probabilities, come from? That requires a look at the 2 phases of training, right?
Exactly. The first is the massive pre-training phase. This is where the model is exposed to literally trillions of tokens of human knowledge. The open web, digitized books, scientific papers, code repositories, everything.
An unbelievable amount of data.
And during this phase, the model's single task is to perform next token prediction. That's it. It's just absorbing language, facts, common sense, and the structure of argumentation implicitly.
It is essentially absorbing the entire library of human thought, not by memorizing facts, but by learning the relationships between every concept within that library.
Correct. The second phase, fine-tuning, is what turns the highly knowledgeable but often unruly pre-trained model into a helpful, usable assistant. This is where it's trained on high-quality, curated examples of human instruction following.
So he learns to be a good chatbot.
It learns to adhere to stylistic norms, respond in a dialogue format, and reject harmful or inappropriate prompts.
And this leads us to the most surprising result of all, emergent capabilities. How does a system trained purely to predict the next token suddenly become proficient at writing Python code or translating Mandarin?
This is the phenomenon of scale. When you train a system on a small amount of data, it gets small capabilities. But when you scale the data and the parameter count to a certain critical threshold, billions upon billions of tokens complex, unexpected abilities spontaneously emerge.
It's like throwing enough data at the system that it can't help but learn the underlying logic.
Precisely. If the training data includes a huge corpus of coding examples, predicting the next token in a code sequence means predicting the next valid line of code, which implicitly teaches the model to program. If it sees millions of paired English and French texts, predicting the next word in the English text forces it to effectively learn to translate. Reasoning, complex instruction following, summarization. They're all implicit outcomes of this simple statistical learning process, just scaled up.
This architecture, the transformer, is revolutionary, but it's not without constraints.
Yeah.
That self-attention mechanism, while powerful, introduced a very serious physical limitation on how much history the model can review. We're talking about the context window constraint.
Yes. Every transformer has a hard limit on the number of tokens it can consider in its input sequence. If your input prompt, plus the history of the conversation, exceeds that limit, say 8,000 tokens, the oldest information just falls off. The model forgets it ever happened.
We've seen these windows grow exponentially, though. From early models barely cracking 2,048 tokens to modern models like GPT-4 offering 128,000 and some rivals pushing toward 200,000. Why is expanding this context window so incredibly challenging?
The answer lies in the quadratic scaling of the attention mechanism.
Quadratic scaling.
If you want the attention mechanism to look at 100 tokens, the calculation is proportional to 100 squared. If you double that to 200 tokens, the calculation doesn't double, it increases by a factor of 4. The computational cost just explodes exponentially as the context length increases.
So while we theoretically could give the model infinite memory, the energy and time required to compute those attention scores would quickly become economically and physically impossible with the current architecture.
That's the constraint that drives so much of the research today. Another critical limitation is the question of true understanding.
Right.
Despite their brilliant performance, LLMs rely only on statistical patterns. They have learned the syntax of truth, but they don't possess symbolic reasoning or true internal world model that's grounded in physical reality.
And this lack of grounding is what gives us the most common failure mode: hallucination.
Absolutely. The model is optimizing for statistical plausibility, not factual fidelity. It knows how a sentence discussing a historical fact should be structured, and it will confidently generate a response that sounds authoritative, even if the underlying fact is completely made up.
It's not lying.
It's not lying. It's merely predicting the most statistically probable sequence of words that fits the prompt, which sometimes just happens to be wrong.
Then there's the very practical constraint of the knowledge cutoff.
Since their knowledge is derived entirely from their pre-training data, they are essentially a static snapshot of the internet up to a certain date. They can't access real-time information or events that occurred after their training was finalized, unless they're augmented with external tools. Their knowledge is inherently dated.
And we have to acknowledge the immense computational costs and barriers these models represent. Training the very largest models costs tens of millions of dollars. It requires access to massive supercomputing clusters. And just running the model still demands substantial GPU resources.
Right, which concentrates innovation power into the hands of only a few large organizations.
It does. But these limitations are driving some of the most exciting future research, largely focused on efficiency and grounding. Let's start with the architectural shift designed to get around the cost of large models. The mixture of experts, MOE.
This is a major change from the traditional monolithic architecture we've discussed.
So explain how MOE works.
Okay, in the classic transformer, when you input a token, every single parameter and every single layer activates to process it, all at once. MOE is an architectural modification where the model is divided into multiple specialized expert subnetworks. Think of it like a committee of specialists.
So instead of all hands on deck for every calculation, we only bring in the relevant specialists for the job.
Precisely. When a token enters a MOE system, a small routing mechanism determines which 2 or 3 expert subnetworks are most relevant to processing that specific token, and only those experts activate. It makes the calculation much, much sparser.
This means a company can build a model with a gargantuan number of total parameters, making it incredibly knowledgeable. But the computational cost to run it is equivalent to running a much smaller model.
Exactly, because only a fraction of the network is active at any given time. It allows for massive scale without a proportional increase in inference costs. It's dramatically changing the economics of running cutting-edge models like Mixtral or GPT-4, which rely on this principle.
Next, let's look at the innovation designed to solve both the knowledge cutoff and the hallucination problem. Retrieval augmented generation, RAG.
RAG directly addresses the static nature of the model's knowledge. When a model uses R, it essentially gains the ability to search a dedicated knowledge base, like a company's internal documents, a live database, or up-to-date web results, before it generates a response.
So the pipeline changes. It retrieves facts, then it reads the facts, and then it generates the response.
Exactly. The model uses that retrieved information to ground its prediction. Instead of guessing a statistically plausible but incorrect fact, it generates a response based on a fresh, verified external document. This substantially reduces hallucination and ensures the information is up to date, overriding the limitations of its original training data.
And we're also seeing the transformer move beyond just text and into multimodal models.
Yes, the foundational mechanism of the transformer self-attention is incredibly versatile. The concept of comparing a query to a key to determine relevance works just as well for processing pixels in an image, frames in a video, or sound waves in audio as it does for tokens.
So the core engine remains the same, but the input data changes, allowing models like GPT-4v and Gemini to seamlessly reason over text, images, and other sensory data all at the same time.
And finally, ongoing research is constantly fighting that computational burden. Key efforts include flash attention, which is an optimization that makes the attention calculation much faster by reorganizing memory usage.
Okay.
Quantization, which reduces memory requirements by running the model using lower numerical precision, fewer bits per number, and distillation, where a large, powerful model is used to train a smaller, more efficient student model to mimic its superior performance. All of it is aimed at greater accessibility and speed.
That brings us to the end of our deep dive into the engine of modern AI. Let's quickly synthesize the core concepts for you, the learner.
First, the flexibility of language is managed by tokens, these subword units that maximize vocabulary efficiency and allow the model to infer the meaning of new words synthetically.
Second, meaning is mapped into geometric space via embeddings. This high-dimensional numerical representation ensures that semantic relationships are captured as physical, mathematical proximities.
Third, the system runs on the transformer, an architecture defined by self-attention, that QKV mechanism, which enables the model to look across massive sequences instantly, synthesizing context for every single token using dozens of specialized heads.
And fourth, this entire system operates through autoregressive generation, where massive scale and relentless next token prediction lead to the spontaneous emergence of complex capabilities like coding, reasoning, and sophisticated human-like dialogue.
Understanding these mechanics, it demystifies the system entirely. LLMs are not a magical black box. They're incredibly sophisticated mathematical constructs, and knowing how they operate allows you to be a more effective, more skeptical, and ultimately a more informed user of this revolutionary technology.
Which brings us to our final, provocative thought. We've established that the entire complexity of the transformer, with all its layers and multi-head attention, is ultimately built upon one conceptually simple task: predicting the most statistically probable next step. It's pattern matching raised to an extreme power.
So if the most advanced technology we have is built entirely on that statistical foundation, optimizing for plausibility over ground truth, how much of what we call human intelligence and reasoning is simply this same highly effective, deeply layered statistical pattern matching system writ large?
And if we acknowledge that the system fundamentally optimizes for coherence and plausibility above all else, what implications does that statistical priority have for the future of knowledge acquisition and the very definition of truth? Something to mull over as you generate your next prompt.
Thank you for joining us.
We'll see you next time.